Welcome to an exploration of one of science's most troubling challenges, the progress paradox. As our research methods become more sophisticated, we can measure more things than ever before. But paradoxically, the gap between what we can measure and what we truly understand keeps growing wider. Let's start by understanding what this paradox really means for modern science. Today, we collect more data in a single day than was generated in entire centuries of human history. We generate approximately 2.5 quintillion bytes of data every single day. Despite this explosion of data, fundamental questions in physics, biology, and social science remain stubbornly unanswered. Here's the paradox visualized. Our data collection capabilities have exploded exponentially, while our understanding has grown much more slowly, creating a massive gap. This creates a dangerous illusion. We feel like we're making progress simply because we're collecting more data. Consider medical research. We can now sequence entire genomes in hours and measure thousands of biomarkers. The human genome contains about 3 billion base pairs that we can now read completely. But despite exponential growth in genomic data, translating this into actual cures remains incredibly challenging. The data grows, but breakthroughs remain rare. This raises a critical question. Why doesn't more data automatically lead to more understanding? The answer lies in what we call the complexity barrier. System complexity often grows as a power of the number of components. Even small systems become impossibly complex. For example, understanding just 10 genes means analyzing not just 10 things, but all their possible interactions. With 10 genes, there are 45 possible pairwise interactions to consider. Scale up to 100 genes, and you're looking at nearly 5,000 interactions. And this is just pairwise interactions. This network shows just 8 nodes with all their connections. The complexity explodes as we add more components, creating a web too dense to fully comprehend. Another major issue is the signal-to-noise problem that worsens with more data. When you measure thousands of variables, you're guaranteed to find patterns by pure chance, even when no real relationship exists. The probability of finding at least one false positive equals 1 minus the quantity 1 minus alpha, raised to the power n, where n is the number of tests. If we use the standard significance level of 0.05 and run 1,000 tests, the probability of at least one false positive approaches 100%. You're virtually guaranteed to find something that looks significant but isn't. In this visualization, the gray dots represent noise, random data points. The red circles are patterns we might mistakenly identify as significant signals hidden in all that noise. This has led to what scientists call the replication crisis. Studies across psychology, medicine, and social sciences show that many published findings simply cannot be reproduced by other researchers. In some fields, the reproducibility rate is as low as 40%. Meaning more than half of published findings may be false. This shows the disturbing reality. A smaller portion of published studies are reproducible, while a larger portion cannot be replicated, suggesting they were false positives or flukes. This raises a troubling question. Are our sophisticated measurement tools actually making science worse rather than better? There's also what we call the abstraction gap between measurement and meaning. Modern instruments let us measure countless proxies and correlates, but not necessarily the fundamental things we actually care about understanding. For example, brain imaging shows us neural activity patterns, but it doesn't directly show us thoughts, consciousness, or subjective experience. The chain of inference is long. Bold signal indicates blood flow, which correlates with neural activity, which somehow relates to thoughts, but the connection weakens at each step. Each arrow represents a leap of inference. We measure something, which proxies for something else, which correlates with another thing, but the actual meaning we seek remains distant and uncertain. Let's look at concrete numbers that illustrate this growing gap. Consider how psychology research has changed from 1960 to 2020. In 1960, a typical psychology study had about 50 participants and measured 5 key variables. By 2020, studies routinely include 5,000 participants and measure 500 different variables. That's a 10,000-fold increase in data collected per study. Paradoxically, the effect sizes we detect have gotten smaller on average, not larger, suggesting we're finding weaker and less meaningful relationships. Average effect sizes dropped from about 0.4 in 1960 studies to around 0.15 in modern studies, indicating weaker real-world significance. Even when we collect perfect data, interpretation remains deeply problematic. Modern machine learning models can make accurate predictions without providing any explanation of why or how they work. Consider a neural network with 1 million adjustable parameters. With 1 million parameters trained on 1 billion data points, the model becomes a black box. Data goes in, predictions come out, but what happens inside the black box remains mysterious. We sacrifice understanding for predictive power. A model might be 95% accurate, but provide zero insight into the underlying mechanisms or causal relationships. Perhaps the biggest gap is between correlation and causation. Our sophisticated statistical methods are brilliant at detecting correlations in massive datasets. But as every scientist knows, correlation is not causation, and this gap persists no matter how much data we collect. Even a correlation of 0.95, nearly perfect, does not imply causation. The arrow doesn't follow logically. A and B might correlate because A causes B, or B causes A, or both are caused by a hidden third factor. Data alone cannot tell us which. This raises a fundamental question. Can we ever truly establish causation from observation alone, or do we need experiments? Let's see how this paradox plays out in real medicine, with life or death consequences. Precision medicine promises treatments perfectly tailored to your unique genetic makeup. However, each person carries millions of genetic variants, creating enormous complexity. A typical person has 4 to 5 million genetic variants compared to the reference genome. Of these millions of variants, we understand the function of only a tiny fraction. Less than 1% of variants are well characterized in terms of their actual biological effects. This visualization shows the enormous gap. All genetic variants form the large blue bar, while the tiny green sliver represents what we actually understand. Here's a powerful analogy that captures the essence of the progress paradox. Imagine we're creating increasingly detailed maps of a territory. Each generation of map has 10 times more data points than the previous one. The old map has few points but captures major features. The new map has vastly more points, but are we understanding the territory better, or just drowning in detail? Eventually, the map becomes as complex as the territory itself, defeating the purpose of having a map. A useful map requires simplification to be greater than detail. Too much detail, and it ceases to be useful. So what can we do about the progress paradox? Are there solutions? First, we need to focus on theory-driven research with specific hypotheses, not data-driven fishing expeditions hoping to find patterns. Second, we must emphasize replication and robustness over novelty. Confirming what we know is as valuable as discovering new things. Third, we should develop interpretable models that explain their reasoning, not just black boxes that happen to be accurate. Scientific value should equal accuracy times interpretability, not just accuracy alone. One promising solution is the pre-registration movement in science. Researchers commit to their specific hypotheses and analysis methods before they ever collect data. This prevents the common practice of data dredging and p-hacking, where researchers test hundreds of hypotheses and only report the significant ones. Pre-registration leads to dramatically reduced false positive rates because you can't change your hypothesis after seeing the data. The workflow is straightforward. Form your hypothesis, register it publicly, then test it. This simple change dramatically improves scientific reliability. Despite all our sophisticated tools, human judgment remains irreplaceable. Algorithms can optimize whatever function we give them, but humans must decide what's worth optimizing in the first place. Deep context and domain expertise remain crucial for interpreting results meaningfully. The human provides judgment, context, and meaning. The machine provides computational power and pattern detection. Neither is sufficient alone. A key lesson is that we must focus on measuring what actually matters. Here's a critical question. Are we measuring things because they're easy to measure, or because they're actually important? This is called the streetlight effect. Like someone searching for keys under a streetlight, not because they lost them there, but because that's where the light is good. The light illuminates one area, so we search there. even though the keys we need are outside in the darkness. Modern science risks the same mistake. Impact does not equal measurability. The most important things are often the hardest to measure. There's also the problem of diminishing returns in measurement precision. Each additional digit of precision in measurement often costs exponentially more in time, money, and resources. Cost is proportional to 10 to the power n, where n is the number of digits of precision. For example, measuring a physical constant to 3 significant digits versus 10 digits. 3 digits might cost $1,000, while 10 digits could cost $10 million. This graph shows cost growing exponentially with precision. At some point, the cost outweighs any benefit from additional precision. Even when we have good measurements, integrating them into coherent understanding is difficult. Different scientific fields measure different aspects using completely different methods and vocabularies. Integrating these measurements requires translation between frameworks, and translation always loses information. When field A's measurements must be translated for field B, meaning gets lost in translation. Each field is like a separate building with its own foundation. The red arrows show difficult bridges we must build between them. The progress paradox also has a crucial time dimension we often ignore. Modern computational methods produce results faster than ever before. However, genuine understanding takes time for reflection and integration that simply cannot be compressed. Data generation might take hours, but developing real understanding takes years of careful thought. Understanding requires time for reflection and integration that cannot be compressed.